In this video, we're going to deduce the structure of an unknown molecule where you're given no relative peak area. So if you look here, we've got C3H9N, and we've just got one singlet at 2.1. Now you can look at the data sheet, for example, and that could give you some information. Okay, or you can think about it in a slightly different way. Okay, so what we'll do is we'll do the thing we always do, which is do the table. Do the chemical shift, peak splitting, peak area. We know we've got one hydrogen environment, just one, okay, and we've got 3 carbons and 9 hydrogens. So that must mean that we've got some form of symmetry in here. So we've got some form of symmetry. That means all these carbons and hydrogens are in the same environment. Carbons with their hydrogens, the hydrogens are all in the same environment. So these 9 hydrogens are all in the same environment. Let's look at this n+1 rule. So n+1 equals 1 means no hydrogens on the adjacent carbon or carbons. Okay, so, or it means that the carbon with the hydrogen on, okay, the carbon with the hydrogen on, that is connected to something that's blocking peak splitting. Now we have an element that's blocking peak splitting. We've got an N, okay, so we've got an N. So that must mean that all of our signals are connected to some form of, connected to that N. So if we then think about that in a little bit more detail, okay, what about if we had a CH3, okay, because, and why do I come up with CH3 as a question? Well, I come up with a CH3 if I come across here and I look at this formula. There's a little tip here, and the little tip is, look at what, if you know that there is one peak, there's nothing else there, look at what this is divisible by. Okay, so you know that you can have a CH3, you can have a CH2, you can have a CH. Okay, it's very unlikely there's going to be 9 CHs, or sorry, it's going to be CHs because look, the carbons and the hydrogens don't mix. And then the carbon and hydrogens are for CH2, again, doesn't work. But CH3s, if you divided that by CH3, that would be 3 CH3s. So it makes sense, maybe that is a CH3. Okay, and if we then do this in terms of the formula, 3 CH3s, as I said, would equal everything but the N. So that kind of makes sense. Now, so if we had 3 CH3s and we had an N, how could we put that into a molecule? So this is why you always do NMR at the end of the organic section, because you're meant to know by that point all of the different functional groups. Well, the functional group I'm going to think about here, if I've only got an N and I've only got CH, and I've got 3 of them, well, I know that nitrogen makes 3 bonds. Okay, so nitrogen makes 3 bonds. So I'm going to bond CH3 here, CH3 here, and a CH3 here. Okay, and just for clarity there's our amine with our lone pair of electrons, which means it can act like a base and accept a proton. Okay, so if that's the case, this is your amine. And if you look here, there is a plane of symmetry down here, down here, down here. All of these are equivalent. They're in the same environment. They're all bonded to an N with 2 CH3s coming out the other side. Okay, so they're all in the same environment. So if that is the case, your functional group in this case is going to be amine. In doing this NMR, we have learned about amines. So for amines, normally though, you would get a slightly broad singlet, and depending on whether it was NH or NH2, you'd have a 1 or a 2 by it for your relative peak area. Okay, but that can also indicate, for example, an amide, because an amide would also give a similar one for the proton on the nitrogen. Okay, but that broad peak here, for example, we've given one with a 1 by it would be an NH. But look for these little singlets for amine groups and amide groups. We also had an example with no relative peak area, which means all the hydrogens must be equivalent. So the big thing is look for symmetry. Okay, so you've got to have something that is symmetrical.